All right, so there's our plan of attack for today. A couple quick notes before we launch into the lesson for today. First one is that all the homeworks for this coming week and the labs have been all set up and opened as of this morning. So we have 2 labs due later this week on differential equations. All the homeworks have been set up. There's homework for 8.1, 8.2, 8.3, and 8.4. We're going to cover section 8.5, but I haven't assigned any homework for 8.5. It's more of a modeling section. So it's going to reinforce some of the stuff we did in the earlier sections. Those problems all tend to be very long. I'm going to skip that section. There will be 2 questions from it on the chapter review assignment. So there's going to be one, I think it's about 15 or 16 questions long, kind of chapter review. And that will be due next Monday. So there won't be an 8.5 section homework, but there will be kind of a chapter review homework. I've also added some extra credit things in Canvas. So this is something I like doing a lot of my classes. It's absolutely optional. You don't have to do it. You have the potential to earn 2% to your final grade, so 2 points to your final grade for the course. In Canvas, it's set up to be its own little group that's worth 2% of your final grade, and then out of a total of 102%. So if you don't do it, it's not going to hurt your grade. If you do, you have a chance to earn 2 points. I put 2 or 3 assignments in there so far. You probably get it to about 6-ish. They're all worth about 5 points. So if you do all 6 and you get good scores on all 6, you can earn your 2%. Otherwise, you'll get some sort of a percentage of that. The ones I posted are going to be related to differential equations. This section, they tend to be bios on mathematicians. So one of them, for instance, is we're going to learn Euler's method in a couple days here. So why is it called Euler's method? Because there's some guy named Leonard Euler. And so you can do a 1-page, 1.5-page kind of Wikipedia web search here to get a little bit of bio information. Just write that up real quick, and that would be an extra credit assignment. I don't tend to grade these very difficult. If you do it, you put some effort into it, I'm going to give you the 5 points. I just like that we kind of look and see who these people are a little bit, just to get a little background. The other one will be a little bit more challenging. It's actually to program Euler's method, so that's an optional extra credit assignment as well. So, any questions about those? For the extra credit, you'll see them in Canvas. They're optional. Don't you see them on Canvas yet? They should be. Oh, yeah, because they don't have a due date. They do have a due date. Let me see if I can find them real quick. I thought I had published them. Make sure I can see them. So they should be these 2, Euler and Euler's method. Does that show up on your syllabus? Okay. So right now these 2 are scheduled for August 1st. That should let us finish this week on differential equations and then give you a full week to see if you want to do them or not. Those will be posted as we go. Okay. Any other questions? All right, so the next thing is an exam 1 discussion. I'm going to be pretty brief with this because I'm going to post a solution key later today. How you have time to look through it, see what you got right, what you got wrong, if you have any questions, and then you can bring those questions to class tomorrow, kind of having looked through the key already. After that, we're going to start our first section on differential equations. So, quick comments about the exam. Class average was 75. The high score was 96, I believe. Like I said, I'm going to post the key later today. A couple of important things to check on this exam. One, add everything up. Make sure I didn't add your points incorrectly. So make sure you check all the points per page. Make sure I did math right on the back. Make sure your score is added up correctly. Also make sure that score on the back of your paper matches the score that's in Canvas. Right? So make sure there weren't any entry errors or anything like that. And after that, once the key is posted, go through and check the ones you got wrong. The same kind of questions will be on the final exam, so you really want to go through this with a fine-tooth comb and make sure you understand why you got what you got wrong. Okay? And there's always the potential that I graded something correctly or didn't give you enough points. So if you have any question about points or why something's marked wrong, feel free to come to my office hours. Happy to talk about things. And I don't get offended when somebody thinks they want more points for something. Happy to talk that stuff out. Okay? All right. So like I said, I'm pretty much going to leave it there. I want you to look through the key, and then I'll answer any questions you might have about the exam tomorrow. Any general questions about the exam? How did it feel when you were taking it? Are there any surprises on there? Was time okay? Have you had enough time? Okay.
I may or may not have went home and had a couple of drinks afterwards. But one of the things I wanted to suggest,
yep.
I mean, obviously, if you're going to post the answers to this later, maybe not this exam, but every other instructor I've ever had, well, the past three classes, they made 1030, 1031, and then 1160, all this, if we could prove that we know how to solve the problem, that we could get half credit for that problem back.
Mm-hmm.
Which I think is a good idea because it's all about, can we actually master this? And like me specifically, 90% of the time, it's an algebraic error. It's
yep.
something really stupid and minuscule, like I forgot a minus sign somewhere, and so
yep. I definitely agree. At the same point, if your algebra's wrong, bridges fall down, right? I mean, when one of the shuttles blew up, and they went back to find out what happened, it was a unit conversion problem. I mean, that's why there was that shuttle wreck that cost, so much money. So the details are very important. I'm all on board with kind of partial credit, and so I really do kind of look through. Now, part of the difference there is that the way I write the exam, I really try to break down the little pieces and the big pieces, so I can grade problems either all the way right or half right, assuming that I've given you credit for basic stuff earlier. So I've already had questions where I'm just having you do the first step, right? So I've kind of giving you your partial credit there to see you've done the first step. But a lot of the problems, I do try to give partial credit if you've done the process correctly. So like I said, on question 3, there's when you're doing these different techniques, there's 2 points for doing that first step correctly, and there's 2 points for finishing the one you decided to finish. That's kind of the partial credit there. On 7, that numerical one, if you had wrong values for left and right, but you decided to do trap using left plus right over 2, I just put a line through it. I didn't actually take off points for it. So you got credit for knowing the process there. Same thing for 10. There was some partial credit if you went through the process correctly but interpreted the limit incorrect. You got 2 out of the 4 points. And then the more challenging part is for the last 2 pages where you're talking about just writing integrals that express things. Because there, it's hard to award partial credit because the features are all kind of the same. It's going to have distance to function. There may or may not be a pi in there. Sometimes it's squared. Sometimes there's a 2 somewhere. So if you know really nothing about how to do any of those techniques, you could probably make it look somewhere in the vicinity, right? Just by throwing a couple functions and 2's and integrating from some obvious limits. So there it's much harder to give partial credit because it might look very similar to the correct answer, but fundamentally be different. Right? So those are kind of challenging to give partial credit to. But in general, my grading style is it's all right or it's half right. I will take like 1 point off if I see a dropped sign or something like that. But for the most part, it's you got it all the way right, or you have the process, so I'll give you half credit, but made some mistakes along the way. So if something was graded differently than that, feel free to bring it and talk through it. Any other questions or comments? I really do appreciate kind of the feedback.
That was nice.
That was nice?
There's just a lot of formulas.
Yeah.
To not have to worry about that.
Yeah, I go back and forth. I mean, I really think it's important to understand where those formulas come from, get the sense of what they mean as distance and rotation and that kind of stuff. But you're right. It's
a time saver too.
Yeah.
You teach this class during the regular school year?
I do. I will be teaching it in the fall, not the spring. Well, maybe the spring this semester. Normally I do a couple Calc 3s in the spring and throw in some linear algebra and some other things every now and then. But next semester I'm taking over as the Calc 2 coordinator, so I'll be writing more exams and kind of overseeing all the sections. So.
How do your average exam scores compare with regular school?
They're pretty much right on the money. In fact, this is a little up, I would say, from the average of all the sections for the last semester. I'd say the average of the averages turns out to be low 70s. So averages on the exam tend to range from, I think last semester our low average was a 67 and our high average was about a 76-ish, somewhere around there. So this falls right in line, in fact a little on the high side. Other questions? All right, so Calc 2 is a tough class, and it's tougher in the summer because it goes much faster. You don't have that soak time for a lot of these concepts. Like you're learning it, you have half a day to practice it, and then we move on to the next topic. So it's much more challenging. So it definitely goes fast. Also, it's a new text, although I think that the exam probably is pretty representative of what you would have seen in the fall or the spring. A bad score on this doesn't seal your fate, though. You can rebound. There's another midterm. There's a final that make up a big chunk of the grade. There's also the labs. The online homework, our scores should be good on that based on the kind of number of attempts and reopen Chapter 6. So you want to use those pieces also to help boost your overall score. Of course, the extra credit now can give you another 2%. So keep fighting. Any other comments? Yep, that'll be the case here as well. Now, I don't think that's entered right now to do that. That's something we do at the end, because otherwise it gives you a false thing, right? We like to have you see the score, and then we drop one and it goes up, as opposed to you do bad in the last one and it goes down and everything's happening. Yep. Yep. I've come back and forth on that policy. The problem is there we have 3 exams, I think, for this semester. So some of that's kind of built in. It's just a little harder in this class to have one drop. So I didn't put that in the syllabus. That's not the policy. Other questions?
Have you taken the chance to listen to some of your lectures using that Bluetooth device?
Yeah, the audio is not very good. No.
Why did you switch to that anyway?
Because the thing I was borrowing, I had to give back. So that's pretty much why. IT let me sample that thing. I'm kind of debating on what I want to actually purchase. That was one of the options. I don't think it's a very good option either, because the audio does go in and out on that as well. Less so, for sure, than the Bluetooth. And the Bluetooth, I mean, this is not really designed for this kind of stuff. It's designed for me running and whatnot. So I am probably going to purchase another Bluetooth headset, one that kind of sits on my head, and has a little pickup mic, like I'm Backstreet Boys or something. So hopefully that will be a little better for the audio. So I'm going to try that next. I can get that relatively cheaply. And if that works, I'll be better. But yeah, the audio is not very good on Bluetooth. Functional, though, I think. I think you can hear most of it. Okay. We'll see how today goes. Today is just the computer microphone, which actually might be better than this in general. It will also fade as I walk out, though. So we'll see how today's goes. I do go back and listen to kind of pick up the audio, but not very much because it's boring. So.
Yeah.
All right. Any other questions? Okay. All right, so differential equations is the topic today. So hopefully you got a chance to kind of read through that first section. It's a lot of introductory material. So we're going to really try to hit on all the pieces here. I don't want to assume too much because I think this is the first time that we've really seen differential equations in this full nature. And it also could be the last time you see it. If you're in a major that doesn't require differential equations, this is it. And differential equations is a very powerful tool, so I want to at least expose you to this stuff. So we're going to try to answer these 5 questions today. What is a differential equation? How do we classify them? What do solutions look like? Because that's not necessarily obvious for differential equations. How do we use differential equations? And then we're going to start on our solution techniques by trying to find graphical solutions. So we'll start off at the beginning. What is a differential equation? So normally we have a pretty complex and long definition, not so much in this case. What's a differential equation? It's an equation that contains derivatives. That's really what they are. They're equations that have derivatives in them. So I've given a couple examples of differential equations here. Now there's a couple pieces I want to talk about specifically with these differential equations. Like here's one. This is an equation, has a derivative, equation, derivative, equation, second derivative, first derivative. So all differential equations. Now in these equations we have 2 variables for all of them. Here, the first one I have a y variable and then a t variable. This y variable we're going to call the dependent variable, dependent, and this t is going to be the independent variable, independent variable. And the idea here is the value of y depends on the value of t. The idea here is this is saying take the derivative of y with respect to t and the result is 2t. So we're kind of assuming that y is a function of t. If y wasn't a function of t, then dy dt would be 0. Right? If y didn't change as t changes, there would be no rate of change of y with respect to t. So those are some important pieces, so I want to make sure we're happy with that definition. Okay, so differential equations are equations that contain derivatives, and in them we're going to have independent and dependent variables. Now, the idea in differential equations, we can't solve them all. This isn't algebra where we just have a couple of set rules and we move them around and we tweak some things and boom, there's a solution. These are harder. Some are going to be easy to solve, some will be very, very difficult to solve, some we're not going to be able to solve. It's just going to be the way they are. So instead of finding some solution techniques for all of them, we're going to try to group them. We're going to say, okay, let's just look at this little group of differential equations. If the differential equation looks like this, now we'll have a solution technique for this group. And we'll look at some different group. What about these ones over here? Well, we'll have a different technique for that group. So a big part of the game for differential equations is classifying them and matching a solution technique with that specific group. So classification becomes very important. So how do we classify them? First way is by order. The order of a differential equation is the order of the highest order derivative. Is the order of the highest order derivative. So the order is a number and it's the highest order derivative that's in the equation. So look at that first example. I have the second derivative of y with respect to x plus the first derivative of y with respect to x equals 4x to the fourth. So I have a first derivative, I have a second derivative. So this becomes a second order differential equation. Because the highest derivative is a second derivative. Any questions about that? Well, the next one, what's the order of that second equation? What's the order of that second equation?
8.
Not quite. It's tempting to say 8, right? Because we have second derivative, we're raising to the fourth power. But what does raising to the fourth power mean? It means taking this thing times this thing times this thing times this thing. That's taking the product of those things, but that's not actually changing the derivative. These are still second derivatives. Doesn't matter how many times I multiply them by each other, They're still just second derivatives. So this is also a second order differential equation. That's a really important distinction here. That this thing is totally different than this thing. The one on the left says second derivative of y. The one on the right says first derivative of y squared. So an example, if y was equal to, let's say, x squared, well then the second derivative with respect to x, first derivative would be 2x, second derivative would be 2. But this side over here, dy dx squared, well the first derivative is 2x, and if I square it, I get 4x squared. So this thing would be 4x squared. So different values or different things here. So be careful with the order of the derivative and raising the powers. They are different things. All right, so that's the first classification. Second classification we're talking about is linearity. Is the differential equation linear or nonlinear? So the book gives you a definition for this. It says a differential equation is linear if the unknown function, that's our y thing, that's our dependent variable, and the derivatives of the dependent variable satisfy these three conditions. They're only raised to the first power. That's one condition. So in other words, I can't have y squared. I can't have y prime squared. They're not composed of other functions, so I can't have sine of y or e raised to the y prime. I can't do any of that stuff. Right. So if you see this stuff, it is not linear, nonlinear. And the last one says they are not present as products or quotients. So in other words, I can't have y times y prime. Even if both of those pieces individually are only to the first power, if we're multiplying, it feels like a second order thing. It feels like a second degree thing. Okay, so none of these things are allowed if our thing is linear, if our differential equation is linear. Questions? Now, it seems like a weird definition, and it is a weird definition. It's not really giving you the definition, it's giving you some symptoms of the definition. Now, so why would they do that and not just give you the definition? Well, it turns out we can take differential equations and write them in terms of differential operators. So in other words, if I had dy dx, it kind of says you have some function y and you are taking the derivative of it. That's what we mean when we write that notation. And so I could take an equation that looks like maybe y double prime plus 2y prime equals 0. And I could really express it as some sort of operation that's attacking my y. I could write it as a second derivative thing here plus 2 times a first derivative thing here. And that's all acting on y. Now don't worry about any of this stuff. You don't need to know any of this stuff. I'm just kind of describing why they mess up the definition. So they call this thing the operator, the differential operator. And we treat it almost like a function that's acting on y. And if that function is linear, if it satisfies linearity as we define it for functions, then we'd call this differential equation linear. So that's more of the real definition. Now, what are the symptoms of that definition? It's all this stuff. All right, this operator is linear, all this stuff is going to be true. Or I guess I should say if all this stuff is true, our operator is going to be linear. Okay? So just know that there is an advanced definition that's more related to the word linear or linearity as you might have seen it in other contexts. But it's a little complicated in this context, so we kind of give you the things specifically to look for. All right, let's see if we got this stuff. Clicker quiz. All right, so I'm going to start the clicker quiz and remind you that we're on frequency DC. Now we're going to start with the first equation, and we're going to answer the first thing here. So for this first equation, what's the order? Is it a first order or a second order differential equation? Is this one first order or second order? Is that first equation a first order or second order differential equation? Alright, looks to be a first order thing. Even though it's square, it's still just taking the first derivative and squaring it. The highest derivative is the first derivative, so it is a first order. So, first order. Alright, now we'll stop that real quick. We'll start another one. Is it linear or nonlinear? Is it linear or nonlinear? Alright, I mixed here. So if it's nonlinear, you should be able to tell me why. So if it's nonlinear, what's the rule that it's breaking? What rule is it breaking? Oh, yep. And I guess that function would be squaring it, right? Yep, so absolutely. So I guess you could think of it in terms of either one of those rules. I'll look back at my rules real quick. Come on, there we go. First one says it's only raised to the first power, so that you can also do that it's raised to the second power, so that doesn't work. But you're right, it's also composed of maybe the squaring function as well. So either way you think about it, it's breaking a rule here. Alright, so that's the problem. It's squared. Right, y equals x squared is not a linear function. Right, kind of to remind us of what linear means in some sense. Okay. Alright, so for the next one, so this one is nonlinear. So nonlinear and first order. What about the second equation? What's this one? Is this first or second order? Alright, second order. Everybody's happy with that. Very good. Alright, now we'll start another one. Is it linear or nonlinear? Alright. Most people say that it is linear. What about this thing? Isn't the cosine a nonlinear thing? Isn't that a curvy guy? You're right, it is linear. Because when we're talking about linear for differential equations, we're only talking about the dependent variable. Just the y. I don't care about this x thing over here. We talk about linearity, we're only talking about the dependent variable. If I look at all my dependent variables, I have y just raised to the first power. That's fine. Y prime just raised to the first power. And the second derivative just raised to the first power. They're not inside of any other functions, cosines or exponentials or logs or anything weird. That is a linear differential equation. So it is linear and it is second order. All right, let's stop. Yep.
Not y double prime unless that's raised to the second power then?
So y double prime means second derivative, not squared.
Okay.
So this says the second derivative all raised to the first power. All right, so I can take the second derivative, third, fourth, fifth, the derivatives. If those derivatives are all raised to the first power, it's still linear. But if I take a first derivative and I square it, it's nonlinear. Okay, so now with the order, we're talking about what's the highest derivative. We totally ignore the powers. We talk about linearity, it's kind of like we're ignoring the derivatives and we're just thinking about the powers. So I can have a fifth derivative as long as it's only raised to the first power. It's not squared or cubed or anything. As long as it's not as the argument of a cosine or an exponential or anything, it should still be good. Make sense? Okay. Yep.
Clarity, I think it's lengthy what he was referring to, but second derivative of y can also be written as dy over d squared, or dy over d.
Yep, I can write this thing right here as d with a little 2y dx like this. Okay.
There isn't the same thing in terms of linearity.
These two things are exactly the same thing as far as notation goes. Right? But this thing is not equal to dy dx squared. These things are not equal. This is a notation for the second derivative. This says take the first derivative and square it. Now I guess using the rules of powers, I could say this is dy squared and dx squared. So it looks very similar. Just that top two is in the wrong spot. But meaning-wise, it's completely different. Does that make sense? So this thing is just Leibniz notation for the second derivative.
Now once you get to like the fourth or the fifth derivative, don't you just put y to the fifth almost?
Sort of, but it's inside of a square bracket to distinguish it from a power.
Okay.
Right? So I could have the fifth derivative of y, which could also be written like this, to the fifth, like that. Have little brackets to denote derivative and not power. Or I could have, this y to the fifth means y times y times y times y times y. And this thing to the fifth means y prime to the fifth means y prime times y prime times y prime times y prime times y prime. And powers and derivatives are really, the notation is kind of similar, but they mean totally different things. This is helping or making it more confusing. Follow-up questions? All right. All right, so what do solutions look like is our next kind of topic, because it's different for differential equations. So let's think about some equations that we're comfortable with, we're used to. Let's talk about this. 2x equals 6. What's a solution to that equation? 3. X equals 3 is a solution. And if I wanted to test to see if it was a solution, I would take that x, I would plug it back in and see if I got a true statement. That's what equation statements are. And it's almost like they're true-false, right? If they're saying that find an x that makes this a true statement. What about this one? Y equals negative 2x plus 4. What would a solution to that thing look like? Could x equal 4 be a solution to that? Not by itself. What would a solution to this equation look like? Let me give me an example of a solution. What is it? I don't have a system of equations yet. To have a system, I'd have to have a couple of these equations. Like I could have a system of linear equations and add a second one, like y2 equals some stuff. Or, give another one. Right now, I just have with the one equation, just a line. If I had 2 lines, you might say, what's the solution to the system, right? I just have 1 line. So I guess let me ask you about a solution. Is that a solution? And if I plug in x equals 2 and y equals 1, I would get 1 equals 0. Right? Not true. So that's not a solution. What would be a solution? 2, 0. 2, 0 would be a solution to this thing. It's a value for x and y that satisfy the equation. When I plug it in, I get a true statement. When I think about what this is, it's a line. And I go 1, 2, 3, 4 up here. Looks like I have a slope of negative 2. Looks like this. All of the points on that line are solutions to this linear equation. And once again, I test them by plugging the values in and see if I get a true statement. Okay. Now, what's the solution to a differential equation? It's a function that satisfies the equation. So a function that satisfies the differential equation, just like here, a point that satisfies the equation is a solution. Here, because we're taking the derivative of that y thing, it's a function. So it's a function that satisfies the equation. So when we start off, before we worry about finding them, we just test for them. So I say here's a function. Is it a solution to this differential equation? And just like our case with the point and the line, I got to plug it in and see if it works. So how do I plug this thing in? Well, my equation says x squared times y double prime. Well, x squared. But what is y double prime? Well, I got to find it. If y is this, then y prime would be 1 over x. Y double prime would be the derivative of 1 over x, which would be negative 1 over x squared. So now I know what y double prime is. It's negative 1 over x squared. The next part of my equation says plus x times y prime. Well, I already calculated y prime. It's 1 over x. And then the question, is this thing equal to 0? And to be true, it has to be true for all x. You can't just say, well, if I pick the most perfect x ever, then yes, it will be true. Nope, it has to be true all the time. It has to be a true statement. So x squared times negative 1 over x squared would be negative 1. And x times 1 over x is positive 1. Does that equal 0? It does. So that means this function is a solution to this differential equation. It is a y, it is a function where if I take its second derivative and multiply by x squared, and I add that to x times its first derivative, I do get 0. And just like if I wanted to plot the solution to a line, I could plot a point. And I could find a different solution and plot a different point. It's kind of like this here. If I wanted to plot a solution, I would be plotting the curve y equals natural log of x. And there might be other solutions, and I would plot them as well. Okay, questions so far? All right, try this one. I did the hard one. You guys get the easier one. Sort of. Is y equals 8x squared a solution to, let's make this really clear since we're talking about it, the second derivative, not the first derivative squared, second derivative of y with respect to x. And let's make it a quicker quiz. A is yes, B is no. Yes, everybody says yes. All right, if I take the derivative, I get 16x. If I take the second derivative, I get 16. Is 16 equal to 16? Sure is. So when I plug this value in to this side, I get 16 equals 16. So it is a true statement. That is a solution. What about this one? Is y equals 8x squared plus 4x a solution? Stop and start. Yes, everyone says yes. Absolutely, if I took two derivatives of 4x, it's going to be 0. So it's not going to affect my final value for y double prime. What if it was 8x squared plus 10x? Would that change anything? Doesn't matter. In fact, 8x squared plus any constant times x would be a solution. So that's an important feature of these differential equations. I'm not just finding one solution, I'm finding families of solutions. Right? I know that 8x squared plus any constant would be a solution. But what about this one? Is y equals 8x squared plus 4x plus 15? Is that a solution? It will, right? The derivative will just kill that 15. So it turns out plus any other constant is also a solution. And that's all the other things I can really add to it. In fact, for this one, because this is kind of a nice differential equation, we can actually find all the solutions to this one. We know how to solve this differential equation already. If I have a second derivative and I want to find out what y is, I'm just going to integrate. If I integrate both sides of this with respect to x, I get dy dx, the first derivative, and I integrate the right-hand side, what do I get? I get 16x plus some constant, right? Plus c is so important in differential equations. It has all the good solutions. So you have to remember your integration, your constants here. That's why we stress it so much. That's why we take the point off, right? It's just a stupid constant. Not for differential equations, it's the whole solution here. Now I want to integrate again. I integrate again. On the left-hand side, I get y. And what do I get on the right side? I integrate the first term. I integrate the x. I get x squared over 2. 16 divided by 2 is 8, so I get 8x squared. When I integrate c1, I get c1 times x. So that's the integral. But I integrated again, so I need a constant. This is a new constant. It's not c1, it's some different constant. So this is really all of the solutions. So I had a whole bunch of single solutions. Here's one solution. This one I'm going to call the general solution. It's got them all. It covers all the solutions here. You choose a value for c1 or c2, it will give you a specific solution. But this kind of captures them all. So in general, we're trying to find the general solution, which represents a family of functions. Okay. Now if I look at this family specifically, I can talk about it has a couple parameters in here. It will change what the solution looks like. Those parameters are those constants, c1 and c2. In this case, it's a two-parameter family. I have an equation that has two constants that I could tweak, maybe to make the solution just how I want it to be, to fit certain conditions. I'm not surprised by that, really. I mean, I had a second order differential equation. In this case, to find our solution, we integrated twice. We integrated once for every order of the differential equation. And that's kind of what's going on here. So I would expect for a second order differential equation to end up with two constants. And that's true in general. So something to note. An nth order differential equation will have n constants in the general solution. So if I was solving a third order differential equation, the solution would look like y equals c1 times some stuff plus c2 times some stuff plus c3 times some stuff. I'd have three constants in my general solution. Now the constants are nice. They let us represent all of the solutions in one nice compact form. But most of the time in real life, I want a specific solution. When I asked for a solution to that line, I didn't want you to say all of the points on the line. I wanted you to give me a specific solution. If I gave you y equals 2x minus 4, I might say, find the solution when x equals 2. I don't care about the whole family, all of the points. I want the one point that also satisfies an extra condition. Same thing here. We have a family of solutions. To pick out a specific solution, we're going to have some extra information. To pick out one point out of the line, I'm going to say which point, oh, by the way, also has an x value of 2. So same thing for differential equations. To find a specific solution out of the family of solutions, we need some information. They need to give us a condition or a point value for every constant. And that condition will look like that function is the thing we're trying to find. So maybe y of 0, when x equals 0, the function value is 2, for instance. That was what an initial condition would look like. But really, they're just giving us a point on the solution. Our solution, a family solution, is a bunch of functions. And this is just saying when x equals 0, y equals 2. So they're giving us one point to kind of identify which function we're talking about. Now, what does this look like maybe more in application? Let's solve a problem here using differential equations, even though we kind of don't have to. We've talked about this problem before. We have a car that's traveling with some velocity. We're driving to Marquette, traveling 50 miles per hour. And now I'm going to talk about my odometer reading. The car initially has an odometer reading of 62,250. Add a couple zeros to one of my cars. What does the car's odometer read after t number of hours? Now, first of all, how would you solve this? Without differential equations, what's the solution? Initial value plus 50 times t. It's an easier problem. We kind of know the solution. And now let's think about it in terms of a differential equation, kind of give us a system for solving problems like this. What I want to know is the miles. If I'm given a velocity, well, luckily there's a relationship between that position value, the number of miles I'm actually traveling, in the velocity. The change in position with respect to time, this is the rate of change of miles, if you will, is equal to 50. Right, the velocity is equal to 50, but velocity is just the derivative of position, so I get this thing. And so I can solve this differential equation. If I want to solve this differential equation, my solution is going to be x as a function of t. And what will my solution be? $50t plus some constant. So if I travel 2 miles, for 2 hours, I'm getting 100 miles to add to my odometer. But if the odometer was different, adding that 100 miles would put me in a different spot. Right? So if I started my trip with 1,000 miles on my odometer, well, then my final odometer reading would be different than if I started with 62,000 some. Okay? So a family of solutions just says add 100 to whatever your previous reading was. That's what my family of solutions look like. But I don't want the family. I want the solution to my specific problem. They gave me my starting odometer reading. They gave me my mileage at time zero. They said when time is 0, your odometer reading is 62,250. So now I can apply that initial condition to find my specific solution. This is how I apply an initial condition to find out my constant. I say, okay, when my t value is 0, so I plug in 0 for t, the resulting x value is 62,250. And then I can solve for my constants. In this case, it's easy to solve for my constants. So it says out of this family of solutions, there's only one that actually satisfies my initial condition. And it's this one. It's 50t plus 62,250. That's the solution that not only satisfies the differential equation. I could check, does this thing satisfy this? Sure, if I take the derivative, I get 50. But not only does it satisfy my differential equation, it also satisfies my initial condition. So this is my solution. This is my specific solution. Okay, any questions so far? Okay, those are all really the big points from this section. Now your book does a really good job of looking at a lot of kind of neat applications, setting up models that are easier to set up. So it will describe a real situation, give you the differential equation, and then work through the family and the specific things. Now there's 2 points I'd like to maybe highlight for your reading. So of course you go back, kind of make sure we understand all the stuff here. I want to point out 2 things. One, example 4 is a really neat application. Example 4, they essentially derive all the equations of motion. So how many people had a physics course in high school or a physics course in college so far? Physics? Okay. Remember the equations of motion? A whole bunch of them. It was like, in fact, we could probably Google it real quick here. Let's see if we can get them. Come on. was like equations of motion. Not motor, motion. I got a 0 in there. Oh, it didn't even work. Equations of motion. I'm not sure what I'll get if I do equators of motion. Equations. That should be kind of close enough, maybe. Okay, good. Yeah, let's see, where are the next ones? You get all these things, right? That's probably what you had in your physics class. So you talk about projectiles being shot into motion, and you wanted to find their position, and you had all these different equations, and I'm sure you probably were able to use your note card in that class, right? You had all these written down, and you had to go through and say, in 10 seconds, where's my projectile? And you go through all this stuff. And these were a pain to memorize. I know they were for me when I had physics. It's like, really? I got to memorize these 10 equations? You know, ugh. But it turns out all these equations are just a solution to one differential equation. All these things really come from is saying, okay, once you launch that projectile, there's only one force acting on that, and that force is gravity. And we can measure gravity, we know what that force is. We also know that acceleration is mass times, force is mass times acceleration. And so the only force acting on our thing is gravity. So gravity looks something like mass times some gravity constant. On the right-hand side, we have mass times acceleration, but acceleration is just the second derivative of position with respect to time. So we cancel our masses out. We write our little constant in here for g, 9.8, and we just solve this differential equation. We'll get a couple of constants in the process, so we'll use some conditions like, oh, at time 0, let the velocity be v sub naught. And at time 0, let the position be x sub naught. Whatever kind of letters you want to use. But if you solve this differential equation, which you guys can actually do at this point, and plug in these values, you get all those equations of motion. That's, of course, how those equations were derived for us. Right? They use some information about a rate of change in real life, and they just solve the differential equation. And it's a very common process. So example 4 goes through all the details about that. I think it's really worth a read, especially if you're doing engineering and you're going to use physics stuff quite a bit. The other note was about the final note in the text. They do a real quick kind of briefing. It's about a paragraph long about existence and uniqueness. And existence and uniqueness. All right, the idea for this is, before we start worrying about trying to find a solution to a differential equation, an important process is to know if you're wasting your time or not. Right, before you start looking for a solution, you need to make sure there is a solution. And so that's a big part of the theory behind differential equations. Say, okay, under what conditions are we sure there's going to be a solution? And if we find a solution, it tends not to be very useful if it's not the only one. So we also want to know when that solution we find is unique. And so this is kind of a classic conceptual question in a lot of fields, differential equations, linear algebra, all that stuff. So real quickly, they just state an existence uniqueness theorem at the end of that section. You don't have to know it, but I just want you to know how important that topic is. Right? That's really the theoretical underpinnings of the differential equation stuff. First, we do a bunch of theory to say, okay, under these circumstances, there for sure is a solution, and when you find it, it's going to be the only one. That makes it really useful to us. Okay? All right, so I would just skim both of those topics second time if you haven't done it the first time. All right. All right, so our last example, we solved this differential equation. And you guys were wonderfully impressed. Woohoo! Differential equations is easy. And we solved it pretty easily because that right-hand side was just a constant. But we could actually solve harder problems. I don't see any reason why we couldn't solve this problem and represent a much more challenging system. Here our rates of change aren't just some nice, wonderful constant, but they're functions. And this is really what differential equation is used for. In that last process, we kind of knew the solution before we even started. Velocity was a constant. We'll just multiply that times the time and you got your distance traveled. But not so in this case. Now we can't just take some rate of change and times some change of time to get our answer, because for every little time step, our rate is changing. Right? We're 50 miles an hour now. Now we're 49 miles an hour. Now we're 62 miles an hour. So that makes everything more complicated. But we still could solve this one. How would we solve this differential equation? How do we solve this differential equation? We integrated twice. Is there any reason we couldn't integrate this thing twice? We know how to integrate e to the x and cosine of x, so we could do that. We could apply our conditions and find our solution. But what if we wanted to model how the population of rabbits changed? Rabbits. Well, how does the population of rabbits change? Well, let's see. So let R be the number of rabbits. This is our population of rabbits number, right? Let's say we have 4 rabbits. Now odds are half of those are male, half of those are females, right? Let's say rabbits on average have 4 babies when they breed. If that's the case, then these 2 rabbits will each have 4 more baby rabbits. Odds are half male, half female. So I'll have 2 more female rabbits over here on each of those. Now originally my population was 4. After one kind of time cycle, let's see, now I have 4 plus 8 is 12. Now if I look at another time cycle, each one of these females will also have another 4. Of course I still have another 2 here and 2 there. So now I'm not adding another 8, I'm adding another 16 to what I previously had. So now I get 28. But once again, if half of these are female, it's going to grow and grow and grow. So I'm not going to add 8 every time. I'm going to add 8. And then I'm going to add 16. And then I'm going to add 32. It's going to grow much faster. So the rate of change is changing. The rate of change is a function. What does the rate of change depend on here? How come I'm having more babies here than I'm having more babies here? Is that? Absolutely. Right? The more rabbits, the more babies they can have. So the idea here is the rate of change of rabbits depends on, is proportional to the number of rabbits. So as a differential equation, it might look like for r, dr dt equals 4r. Well, what's the problem with this differential equation? Why is this one any different than the last one? Can't I just integrate? Let's go back to our nice notation. We don't like r's and t's, we like y's and x's. This looks like dy dx equals 4y. Why is this harder? Constant doesn't change it too much. I have this 4 here, but if I were to integrate, 4 would just come out, right? So that shouldn't really hurt me too much. The problem is the y. We just said before, let's just integrate, right? If I have dy dx, I can just integrate, I'll get to y, right? But when I do that,
the inverse of that. So like if you were to take it as with respect to x as opposed to y.
I think you got the right problem, not the right solution yet. But why would you have to do that?
Because you can't, because y is your dependent variable.
Absolutely. But when I say I'm integrating, I should say I'm integrating with respect to x. If I have the derivative with respect to x, I have to integrate with respect to get back to y. But that leaves me on this side integrating some function y with respect to x. I don't know how to do that. And this isn't like y squared over 2. I can't treat y like it's a constant because y is a function of x. I don't know what that function is. That's why I'm trying to find a solution. Y might end up to equal cosine of x. But until I figure out what that y is, I don't know how to do this integration. So that's why this is a problem. That's what differential equations is all about. We've seen the easy problems, right, if the rate of change is a constant, or even a function of the independent variable, we just integrate. No problem. The problem is we might also have dependent variables over here as well. How do we deal with that? That's the hard part. That's the real study of differential equations. If I go down here a little farther, what about these problems? Right? dy dx equals y squared minus sine of y. Second derivative plus 2y prime plus y equals x. I have independent and dependent variables. These are hard problems. These are differential equations. I mean, up in this case, I might actually be able to solve this thing if we think about it. Now, let's get rid of the 4 just to make it a little simpler. dr dt equals r. My solution is r, some function of t. I need a function whose derivative is the function. Anybody know a function like that? E to the x, absolutely. In this case, e to the t. Is e to the t a solution? Well, then we could test it. The derivative is e to the t, r is e to the t, those things are equal. This is a solution. So this nice case, even though it is more complicated, I can kind of guess my way to a solution. But obviously with these ones, I'm not going to be able to do that. These ones are much more challenging. All right. So all that being said, how do we solve these things? How are we going to solve these differential equations? Well, like we said at the beginning, it's hard. It is not a trivial thing. This is not algebra. This is differential equations. So we're not going to be able to solve all these. But what we are going to do is try to get them in groups that we can solve. We're going to classify them by order, classify them by linearity, and find techniques to solving them. But even the ones that we can't solve, we can still solve. Even if we can't go through some process to find a mechanical solution, analytic solution, we still might be able to approximate a solution or visually see a solution. So just like when we talked about stuff in high school, linear equations, there were multiple techniques for solving it. Same thing for derivatives or integration. We have different methods for solving these things. We want to look at all three of these because they're going to complement each other. We want to solve differential equations graphically, numerically, and analytically. And they all have strengths or weaknesses. Graphically is quick. It's easy. Throw up a plot. Say, oh yeah, when I get over to here, my solution looks like this. Woohoo! But there's some limitations with a graphical solution. Anybody think of any limitations? I look at a plot and say, right there. Am I pretty accurate when I do that? Not necessarily. You're always approximating there, and it can be a pretty bad approximation when you do that. Numerically, it's kind of the same thing. Numerically is a process that will work. It might take a lot of computation, but I can program that. But once again, it's approximating some real solution. Analytically, it's hard. Right? It might be impossible. But if I can find that solution, it's a very general solution. It always works. It gives me an exact value. So there's an advantage and disadvantage to each of these. We want to start off by talking about solutions graphically. So we're also going to start off, and differential equations is a broad topic. Of course, there's courses passed here on just differential equations. So we're only going to look at small groups here in our one little chapter we have to introduce you to it. So we're only going to talk about first order differential equations from here on out. Okay? So we're already looking at our first little subgroup to see if we can just work with our subgroup. We're just going to be looking at first order differential equations. And one of the advantages of first order differential equations is we really have this graphical approach. How do I look at this differential equation graphically? Well, what this differential equation tells me, it doesn't give me the function, but whatever the function is, it says the slope of that function is equal to 2x. So I don't know the value of the function everywhere, but I do know its slope everywhere. So how does that help me? Well, I'm going to sketch a little coordinate system. Well, that's crooked as can be. It's a little better. So here's what I could do. I could say, I don't know the value of the function everywhere, but I do know the value of the slope everywhere. Right? The slope is given to me on this right-hand side. In general, our differential equations will look like this, our first-order differential equations. It says slope is equal to some stuff on the right that has x's and y's in it. That's what f of x, y means. It says. So it could be all kinds of junk over there, and it could be a function of both x's and y's. So I have kind of an easier problem here. If I were to go to some random point, I am picking this out at random, the point 1, 1. If my solution went through that point, what would the slope at that point be? What would it be? Not 2x. So this is our slope in general. Right? If our solution looked like this, our slope at all those different points could be represented by this. If I wanted to find the slope along this curve right here, I would say, well, when x is -3, our slope is, and plug that thing in. Now what I'm saying here is, I don't know what the function is, but I can still look at this point. This point is x equals 1, y equals 1. So the slope in general might be 2x, but the slope here is what? 2. It's 2 times x equals 1. So at this point where x equals 1, y equals 1, my slope is just a value of 2. Okay? So I'm going to draw a little line that looks kind of like it might have a slope of 2. There it is. That looks like a line with a slope of 2. All right, little arrow. And then I'm going to pick a different spot. What happens if I'm at over here? 2, 1. What would the slope there be? Right over here. X equals 2, y equals 1. 4. So it's a little steeper. Okay. The thing I'm going to draw is a slope field, or your book calls it a directional diagram. And all it is me plotting the slopes everywhere. That sounds like a lot of fun, doesn't it? Let's go to all these other points and keep drawing lines. That's really what we could do. If I went to this point, this is the point x equals 1, y equals 2. What's the slope there? 2. Well, that makes sense. It's got to be the same as this. I didn't change my x value. I only changed my y value. And there aren't any y's in my expression. So actually, I could draw all these slopes going up. The slope will always be 2. So all I'm doing is changing the y value, not the x value. That's just a coincidence here. That's just the nature of this function specifically. But it lets me shortcut a bunch of drawings, right? These are all going to be a little steeper. These are all going to be like this. If I go farther over, now I have a slope of 6. That's even steeper yet. If I'm right here at x equals 0, y equals 0, what would my slope there be? 0. So I have horizontal slopes all there. Over here at -1, I have a slope of -2. Drawing all those slopes. -2. Now we just draw all this stuff out. And you say, well, that's an interesting picture. But it's actually a useful picture too. Now I don't know what my function is, but now I know how it moves. If my function did go through this point, I would know it would be traveling in this direction. So let's pretend it travels in that direction a little while. Well, then if it goes through this point, it would be traveling in this direction. So I can kind of follow these little lines around to sketch out what my function might look like. My function might look something like that. And that makes sense here, because for this easy differential equation, I can actually solve this. What is the solution here? Y equals x squared plus some constant. Could be any constant, right? Any constant here will work. Great, I can see all of those here. I can see all of these solutions, the whole family, in my one picture. Because what I did was I said, well, what if my solution happens to go through this point? But it didn't have to. It could have gone through this point, or this point, or this point, or any of these points. So which one I drew, if I started here and drew it, it would look like this. If I started here and drew it, it would look like this. But all that is x squared plus some constant. So this slope field shows me all of my solutions. All I have to do is follow the flow through the field. Start at some point, follow the flow. So here's a differential equation. I found my general solution. If I wanted to find a specific solution, what would they have to give me? Initial condition, which might look something like this. Y of 0 equals 2. And I could use that to analytically find out what C has to be. But remember, this just tells me x equals 0, y equals 2. That's just a point. That's the point 0, 2 right here. This is the solution that satisfies that initial condition. So even the initial conditions have a very physical representation on my graph. It's the one point that our function is going through. And because this is a first order differential equation, I only need one point. I know kind of what they all look like. I know all their shapes because of the differential equation. And now I know one point it goes through thanks to the initial condition. Okay. Any questions so far? Now, what do we want to learn from slope fields? They let us approximate solutions. Just looking at the slope field, I was able to sketch out what looked to be a parabola. Okay, so that was useful. Even if I couldn't identify it as a parabola, I could approximate certain solution values later. If my initial condition was y of 0 equals 2, I could probably guess what y of 2 is equal to. I could probably guess what my solution looked like at a specific time. I can also identify key features of my model. Right? Are there important initial conditions? What happens in long-term behavior? What happens as time goes to infinity? I can also talk about special cases to make this graph even more useful. Now, the only problem with all this stuff is that all these problems start with us making a slope field, which, as you just saw, is not very fun. So, of course, we don't want to do that. We want to let Mathematica do that for us, because we don't want to go to every single point and plot it. And even if we could, I was just going to 1, 1 and 2, 1. What about a half and 3/4? What about that point? That might have a different slope as well. So let's learn how to do some of this stuff in Mathematica. All right, you have 2 labs due at the end of the week. One is an introduction to differential equations. One involves slope fields. I'm going to go through a lot of their content here. It won't be written up the same way, but I'm going to use some of it. So let's get rid of this first of all. All right, so there's a differential equation, for instance. A couple things I want to be able to do. First, I want to be able to solve it in Mathematica. Mathematica should be able to solve it for me. And then 2, I want to look at these slope fields. So real quick, just so you've kind of seen the command before, to solve it, the command is dsolve. It says put in your differential equation and then put it in the variable name. So I'm going to say y prime of x. Now we talked about y being the dependent variable, so y is a function of x. Mathematica does not take that for granted. So if you write out your differential equation, you need to show that it depends on x. You need to write of x every time you use that y. So this differential equation looks like double equal sign, because we're asking the question, we're not assigning a value, x minus y of x. And then it says give me your dependent variable and your independent variable. There's my dependent variable, there's my independent variable. And the lab will walk you through this all in steps. But it will give me my solution. There's my solution. And in fact, if I want to add an initial condition, all I do is put in a list of equations. So instead of just putting in the one equation, put in more than one. Put in y of 0 equals 4. And what will happen is, Ah, so you guys can't see anything over here. Over here, you can kind of see stuff. That's lovely. You see that better? Okay. So there's a constant in my solution. I expect that, right? That's that one constant in my solution. But if I put in the initial condition and rerun it, it will take care of that constant. It'll figure out what it needs to be. Now what I want to do is also look at vector plot. So I'm going to use the command vector plot. Once again, this is all spelled out in your lab. Vector plot says plot a vector at a whole bunch of different points. So it's going to take 3 arguments. 1, what is the vector? 2, what is the range of x and y values? So 5. It says how big of a plot do you want, essentially. Now, how do I enter in the vector? This is kind of the weird piece. Well, the idea is this. I know the slope everywhere. So if I went some point, like 1, 0, the slope would be 2. Okay? Now what I want to do in my vector plot is draw a vector with a slope of 2. Well, slope of 2 means it has a rise over a run of 2. If I make a vector that has a 2 here and a 1 here, that says go over 1, go up 2. And we have a slope of 2. If I wanted to have a vector that had a slope of 50, I could do 150 over 1 up 50. So because my slope is this function here, I could write the vector 1 comma 2x. And that should give me the correct slope at all the different points. So in general, I want to go 1 comma and whatever the right-hand side is of my differential equation. In this case, it's x minus y. And this will give me my vector plot. So give me my slope field diagram. And now I can see kind of the solutions. And so now I can investigate all I need to investigate with this graph stuff. Now there's a couple things here that we want to tweak a little bit. Because the vector plot's like a relative length of the vectors, it's going to have some long ones and have some really little ones that are hard to see. So if you have a situation like that where it's hard to see what's going on, there's 2 things you can do. You can scale the vector. So instead of plotting this vector, I'm going to plot a unit vector. Ooh, how do I make a unit vector? Well, I take a vector and divide by its length. In Mathematica, the command for length is norm. Now they all have a length of 1. So I can kind of see what happens a little better. That still bothers me because they still look a little big to me. So I will also use vector scale and make them tiny. And that kind of gives me a nice one that I like to look at. Now once again, the lab will walk through these options. I feel bad because you guys can't really see this over here. But we're going to want to look at these slope fields and talk about what solutions look like. If I started here as an initial condition, I have to follow the arrows to see what's going on here. And so we'll talk about a bunch of these vector plots tomorrow. We'll also talk about some numerical techniques. So for tomorrow, review section 8.1 as needed. So if you were prepared for today and already read through 8.1, should have been kind of a class review and you should feel pretty confident. If you didn't, well then take the class time, stuff you learned today, and go back and reread that section. Okay? But for tomorrow, read section 8.2 and 8.3. We'll get all the way through 8.2 and hopefully we'll get into 8.3 a decent amount. And then start looking over the homeworks and office hours right now.
I have a question.
Yep.
Can I get the lectures that you have by email or